Hello, my name's Garrett Flowers, and I'll be presenting on my research of predicting Colorado River streamflow. Climate change stands as one of the most pressing environmental challenges of our time, with widespread consequences that impact ecosystems, economies, and communities alike. Water resources are among the most critical aspect affected, facing increasing strain as global temperatures rise and precipitation patterns shift. In Colorado, where river systems are the lifeblood of both urban and rural communities, these changes are particularly significant. Approximately 83% of Colorado's drinking water comes from river systems, which also provide vital water resources to several downstream states, including Arizona, Nevada, and California. The impacts of climate change are already evident in Colorado's river systems, as stream flows have decreased by an estimated 3 to 19% since 2000 compared to the historical average from 1951 to 2000. This decline is driven by diminished snowpack, earlier snowmelt, and altered precipitation patterns, and it is expected to worsen, further straining water supplies. The primary objective of this research is to develop a predictive model capable of accurately forecasting river flow in the Colorado River Basin. Such a model would serve as an invaluable tool for water managers tasked with making critical decisions about water allocation, drought mitigation, and long-term resource planning. By integrating climate projections with historical data, the model aims to provide actionable insights to help mitigate water shortages and ensure equitable distribution among stakeholders. Although extensive research has explored the impacts of climate change on water resources in Colorado, there remains a gap in the application of machine learning specifically for river flow prediction in the Colorado River Basin. This project aims to fill that gap by analyzing the complex interactions between snowpack, snowmelt, precipitation, and temperature, and their combined effects on river flow and water supply. Historical data used in this research include precipitation, temperature, snow, and snow water equivalent measures, along with soil moisture and stream flow. Along with that, we use RCP scenario data, which originates from the Working Group on Coupled Modeling, who puts together the Coupled Model Intercomparison Project data, also known as CMIP. These climate models have very low resolution and span the entire globe. Therefore, other smaller, more targeted institutions, such as the Canadian Center for Climate Modeling and Analysis, publish a higher resolution data set for North America, and it's called CORDAX. This will be the data used to model our RCP scenarios. Regarding RCP scenarios, here is a comparison chart to explain what we are working with. I've selected the 4.5 and 8.5 scenarios, which are based on varying trends of CO2 in the atmosphere. So 4.5 is going to be kind of middle of the road in regards to CO2 in the atmosphere, and 8.5 is going to be an extreme situation, worst case scenario. From here, scientists are able to produce various meteorological and climate effects, which I will be using in the research. But back to historical data. This analysis is highly sensitive to geographic location. For instance, if I pull temperature data from a USGS station 100 miles downstream of where I'm measuring stream flow, we will have a very difficult time mapping out any type of relationship between those two variables. The locations chosen were strategic. The Colorado River location was selected due to the convergence of several smaller streams and rivers. The snowpack and snowmelt high up in elevation at the McClure Pass and Bison Lake stations also make a large impact to the overall stream flow levels of the Colorado River. For the CORDAX RCP data, we perform a latitude-longitude slice that covers the exact geographic bounds of the state of Colorado. The state is a rectangle, so it's pretty easy to do. Onto the modeling. So in the research, we use several machine learning techniques to build up a robust RCP-based data set used to predict stream flow. Using temperature and precipitation, we use a random forest approach to identify a binary label for snow on that particular daily record. Based on several earlier analyses within the research, it was found that soil moisture at the 8-foot level had the best ability to affect stream flow. This may be due to the fact that 8-foot measurements had the most complete data available, whereas the 20-foot or the shallower 2 to 4-foot measures were much more incomplete. So I'm going to transition into more of the results and start to talk about conclusions now. So up on the right side of the screen are two pieces of the puzzle, the snow label prediction and the soil moisture, which will feed our final model. Overall, the random forest approach does a great job of mapping snow labels, and we can be fairly confident of interpreting the results in our later steps. The LSTM model, we are trying to predict a continuous value, so it can be a little bit more difficult, but overall does a fairly good job at capturing shifts in soil moisture despite some data limitations. And we will rely on these results for our final streamflow prediction. Now here is a performance summary of the LSTM neural network ensemble for Streamflow. The model struggles to capture the extremes, as you can tell based on the chart. And this is most likely due to the ensemble and regression averaging approach. To risk not overfitting the data, we accept the results and just note the limitation of interpretation here. We can't use the results to predict extreme events in the future, but we can use it to get a general sense of averages over time. The model does a good job of capturing this. Moving on to the RCP scenario results. I will display snow and soil moisture results here, then finally conclude with the RCP streamflow predictions and some various graphics. So using the random forest ensemble approach for snow, we are able to apply the model prediction to both RCP 4.5 and 8.5, which are the moderate and severe climate projections. The results generally make sense. We see an overall decreasing trend as temperature is expected to rise in both RCP 4.5 and 8.5. There are less snow days on average in the RCP 8.5 scenario compared to the RCP 4.5 scenario. Next, we apply the LSTM model to soil moisture. The model is generally able to pick up trends of how soil moisture changes over time. Soil moisture is a key component of streamflow. So we apply the LSTM models to the RCP scenario data here. And under RCP 4.5, we observe a flat to slightly positive trend. It's possible we're getting signal that increased temperature may cause earlier snow melt, resulting in a slightly more moist, but also more volatile environment. Under RCP 8.5, we see a clear downward trend that indicates drier soil up till 2100. Utilizing an LSTM ensemble approach, we are able to capture a decent amount of volatility in our streamflow testing data. In general, the model, as I've said, does a poor job at predicting the extreme swings for both the high and low cubic feet per second streamflow measure. However, the model may be useful to uncover hidden broader trends on average, rather than helping to predict extreme events. Therefore, we aggregate results at the yearly level to see if we can uncover any useful trends of streamflow over time. Based on increasing temperatures, fewer snow days, and generally decreasing soil moisture, we see the effects of climate change play out in our model data. The overall trend suggests that mean streamflow will decrease in the next 70 to 80 years, indicating a potential real problem for our downstream states that rely on this water. Lastly, we took a look at the yearly seasonality and how it may shift given projected higher temperatures. Based on the above graphs, one can observe the model's inability to predict the extremes of peak streamflow, especially into the winter months. However, the model does give us some indication that early to late spring may produce higher streamflows on average due to earlier snow melt, experience drier than normal conditions in the summer, and then fail to produce historically peak streamflows going into the winter months. Thank you all for listening.